In this video, we're going to finish up Chapter 6 by talking about the binomial distribution. So in the last video, we talked about the normal distribution, its sort of properties, qualities, and how to find probabilities about something that has a normal distribution or is normally distributed. Now we're going to talk about the binomial distribution. So unlike the normal distribution, the binomial distribution is a discrete probability distribution that gives the probabilities for counts with binary data. Okay, so what does that mean, or what sort of implications does that have? Well, it is a number of sequential trials of things or situations where only two possible outcomes that can happen, a 0 or a 1, a yes or a no, a success or a failure. And so a sequence of those trials makes up a binomial distribution, okay? Or the binomial distribution is about those sequence of trials. And so you can think that the binomial distribution, it's sort of like basic situation in which you would use that is for flipping coins. Okay, so it's a sequence of coin flips, sort of. So a random variable that has a binomial distribution will always be counting the number of successes out of n Bernoulli trials. Okay, so there's a lot to unpack here. For the normal distribution, there are a variety of situations in which I could say that that is a normal distribution. It could be on heights of people or weights of people or really anything. But there's a little bit more of a restrictive definition for a binomial distribution. The random variable that we're going to see, which we usually call capital X, is always going to be counting the number of successes out of n trials. Okay, and we'll talk about a little bit about what Bernoulli trials are in just a second. So there are three conditions that need to be met in order for us to be able to use the binomial distribution. Okay, so there are three conditions. The conditions are that each trial that we have has only two possible outcomes. And that means it's a Bernoulli trial. So a Bernoulli trial is a trial with only two possible outcomes. So that means if you flip a coin, heads or tails, success or failure, 0 or 1, okay, anything that has two outcomes, each trial has to have the same probability of success. Okay, so as the trials go on, they can't have different probabilities. So a situation that's often used for the binomial distribution when you talk about it is shooting free throws in a basketball game. And so you have some set probability of success, and each time that you shoot, that probability of success stays the same for each time. Now, you can argue that in truth, it's not the same for every time, and as you shoot a bunch of them, you'll get tired and the probability will go down, or it'll go up because you're more, your muscle memory has sort of built up, so on and so forth. But we're going to believe that, or what we're going to look for here, is that the probability of success stays the same the entire time. Okay, this is easily seen also with a coin. The probability of flipping a coin and it landing on heads is 1/2 each time, if it's a fair coin, of course. All right, and so that's number two. The third one is that each trial is independent. Each trial is independent, which means that the first flip of the coin has nothing to do with the outcome of the second, or the outcome of the third, or the first 975 flips don't affect that 976th. Okay, so that's what it means for the trials to be independent of each other. Once those three things are met, then we can use the binomial distribution to talk about or describe a situation. Okay, so here are the properties of a binomial random variable. Okay, so a binomial random variable is parameterized or characterized, as I just as before, if you remember back to the normal distribution, it is characterized or parameterized by mu, the mean, and sigma, the standard deviation. In the case of the binomial distribution, the two things are the number of trials, n, and the probability of success, p. Okay, so we need to know how many flips there are and what the probability of success is for each flip. Okay, and so hence we need that 1p, which is also why we need that condition that the probability never changes throughout the flips. Okay, it's denoted as always x tilde, which means x is distributed as, instead of the n for normal, we put bin for binomial. Okay, and then inside the parentheses are where the two parameters go, n and p. Okay, it has, and this really should say PMF instead of PDF. It has a PMF of this form. Okay, and so for the normal distribution, there was really no way to talk about why that formula was the way it was, other than somebody brilliant came up with it at some time. But the idea behind the binomial distribution PMF, which gets us the probability of any one thing happening throughout, so the PMF is the probability that x equals x. So for instance, if I wanted to see out of 10 coin flips, what's the probability that I get 5 heads and 5 tails, I could use this formula here to tell me what it is. Okay, it would give me the probability back. And so you can really split this PMF up into 3 parts. The first part is n, and then there's an x under it, and then there's big parentheses around it. That is, you would say that as n choose x. N choose x, okay, which is a choice operator, which is in probability theory type things, okay? And so there's a formula for that. N choose x is really n factorial divided by x factorial times n minus x factorial. So it's a little complicated, okay? But that's the first part. We'll come back to that. P raised to the x power is the probability of success raised to the number of successes that you're going to have. Okay, so if I expect 5 successes, that's it would be, and it's a coin flip, so p would be 0.5. That's 0.5 raised to the 5th power. And then the second part, 1 minus p to the n minus x, 1 minus p is the probability of failure. If p is the probability of success, there are only 2 possible things. Everything else must go with failure. And so 1 minus p is the probability of failure raised to n minus x, which is the total number of trials minus successes, which is failures. Okay, so n minus x is the number of failures. So it's the probability of failure raised by the number of failures, raised to the number of failures. So we have p to the x times 1 minus p to the n minus x. Okay, that is hopefully makes some sense to you. And then you have n choose x in front. That's how many ways I can get however many successes and however many failures out of the n trials. Okay, so if that can happen only one way, then that n choose x would be 1. But if it can happen a number of different ways, which I could, for instance, if I had 3 successes and 7 failures, that can happen a bunch of different ways. That n choose x out in the front is going to tell me how many ways that can happen, and that of course influences the probability. Okay, so a long-winded definition or explanation of the PMF, but hopefully that makes sense. And then every distribution has almost all of them have a mean and a standard deviation. Okay, and so this is, sorry, a telephone is ringing. The mean and standard deviation, sorry, I'll wait until the telephone stops ringing. Okay, so the mean and standard deviation, almost all distributions have it. Something that's weird about this is I say the mean is mu and the standard deviation is sigma. Those are the symbols that we use for all means and all standard deviations. But for the normal distribution, we also use mu and sigma as well for mean and standard deviation. But that's for like specifically the mean. So don't get confused, or don't think too much rather about the symbols. But the binomial distribution has a mean of n times p and a standard deviation of the square root of n times p times 1 minus p. Okay? And you can also think a little bit about those and make some connections in your head. If I told you, if I flipped a coin 10 times, how many heads would you expect if the coin is fair? You would say 5. And so how did you get that? Well, you sort of have an idea about what's going on in your head, but we can also do that explicitly here. If I had 10 trials, n times the probability of success p, 0.5, 10 times 0.5 is 5. And so 5 is the mean, okay, which is what you would expect. And so hopefully that matches, your intuition matches the mathematical formula for the expected value. Okay? All right, so a few notes about the binomial distribution. When n becomes large enough, when I have a large enough trials, something interesting happens. The binomial distribution starts to look like the normal distribution. So that may be odd for you, and rightly so, because you should say, the binomial distribution is a discrete one and the normal is continuous. So how can something discrete start to look continuous? Well, there are many ways that can happen, but the histogram of the different values from the binomial distribution will start to form something that looks like a normal curve. Okay? This is often called the normal approximation of the binomial. Okay? And it was historically useful because for large n, the probabilities that we saw, or the formula for calculating the binomial probabilities, became really tedious and really hard to compute. Okay? But they had that normal table, they had normal calculations already. So that was really early on that they were able to calculate stuff about the normal distribution. So this was useful. Instead of using the binomial formula, I could just use the normal approximation to the binomial. Okay? But this usefulness has gone away because of the computational power of the modern computer. There's no need to use something that's an approximation when I can do the exact thing. Okay? So here's a your turn, and it's similar to the last your turn, but now it's a binomial. Okay, so I know I haven't done an example, but this should be fairly straightforward. Instead of normal on Minitab, you're going to choose binomial. And so I'll go through this and I'll actually answer the first one with Minitab just to give you an idea of what it looks like. Okay, so suppose I flip a coin, fair coin, 50 times. Okay, and I'm counting X, the number of heads that lands. Okay, so first answer the binomial conditions. Are they satisfied? You have to answer that. I won't answer it for you. Okay. Then I'll ask what is the distribution of X. Okay. Then we'll ask a number of questions here. Okay. So less than 20, less than or equal 20, and then between, including 30 and 40. So quickly here, I'll open up Minitab. Okay, and we'll go to calculate probability distributions, cumulative probability. Okay, and then I'm looking for the binomial distribution, which is up here at the top. Okay, binomial distribution. I'm still looking for a single value here. The single value is, well, we have to make sure, we have to think about this, but 20 is the number that's put in there, okay? Binomial number of trials is 50. Probability of the event happening is, well, if it's a fair coin, it's 0.5. So that answers some of the first couple questions, okay? And so if I click OK, it says for 20, the probability that x is less than or equal to x is 0.101. So actually that answered the second question, okay? Less than or equal to. The first question is less than 20. And for discrete distributions, that answer is different. In continuous distributions, the answer would be the same. But for the binomial distribution, this answer is different. So I'll leave you to figure out what to do for less than 20. Okay? And then for between 30 and 40 inclusive, you also have to do two calculations for that. But we sort of talked today, or talked in class, about how to handle these in-between situations. Okay, so that's the end of the end of chapter 6.